Hey folks, we're going to look at the graphs of the sine and cosine functions and see where they come from. Now we're not going to do all the transformations, we're just going to graph the basic sine of theta. And so what we need to do first is we need to remind ourselves what sine is. Sine forever has been opposite over hypotenuse, which we redefined on the coordinate plane. We said that opposite side, that's like the y-coordinate, and the hypotenuse is like the radius. Now, the unit circle is particularly helpful for graphing sine of theta because r is 1. Meaning, all I need to do, if r is 1, anything over 1 is itself. So to graph sine of theta, I just need to look at the y-coordinate for any given angle, theta. And so here's where we're going to start with our unit circle, which we've derived in a previous video. And what we're going to do is we're going to start and we're going to say that, okay, for 0 radians of rotation, we'll do this whole thing in radians, sine of theta would be the y-coordinate at 0 radians of rotation. The y-coordinate there is 0. So for 0 degrees of rotation, sine of theta is 0. But then we move to pi over 2. So if I travel my unit circle to where there's pi over 2 or 90 degrees, our y-coordinate there is 1. So for pi over 2, it's 1. And then we get to pi radians. Well, if I keep traveling around to pi radians, aka 180 degrees, it looks like our y-coordinate is back to 0. And then if we go to 3 pi over 2, it's kind of getting cut off down here at the bottom of my unit circle, but at 3 pi over 2, aka 270 degrees, that y-coordinate's -1. And then we get back to 2 pi, which is coterminal with 0 radians, so we are back to 0. So what we have here is we have these points, and what this is going to look like when we graph is it's going to go and it makes this wave because that y-coordinate is going to increase until it gets to that peak, and then it's going to decrease as we continue to rotate around that unit circle. And then in this fourth quadrant, it's going to increase back to here. And so what we would do is I just want to answer a few quick questions about the sine function. The period of the sine function is 2 pi. That's how long it takes to repeat. If we were talking in degrees, it would be 360 degrees. Because after we do our full revolution around the unit circle, we're just doing the same thing over and over and over again. This is going to continue on forever. The amplitude is the distance above and below this midline. So if I picture this kind of highlighted green line as the midline down the middle, the amplitude is how far above it and how far below it this travels. And in this amplitude is 1. Our maximum is at 1, our minimum is at -1, but we always define that amplitude as a positive. So our amplitude here is 1. Now the domain, as I said, we're showing 2 pi here for our x's, but this graph could keep going on forever. It's going to keep going forever to the right, and it's going to keep going forever to the left. So our domain is all real numbers. And then lastly, our range is the set of all the y-coordinates. If you look, our minimum y-coordinate looks like it gets down to -1. It's going to go down, it's going to hit that -1, and then it's going to go as high as a maximum of +1. So that's going to be our maximum. So this is the period, amplitude, domain, and range. Now my next thing is I've got a little interactive applet that I want to show you. The link's right there, but I'll go ahead and put the link to this in the show notes. This is not something I created, so I want to make sure and cite my source here. But I think this is going to help us visualize what's happening maybe a little bit better than what I did on the last slide. So we're going to start with our sine graph, okay? And what I'm going to do is I'm going to drag this to show the rotation. You can see that I'm dragging this, and we get up to that peak of 1. And then the red represents that y-coordinate. That's what we're graphing. We're graphing the y-coordinate. It's going to go back down to 0. And then as I continue to rotate, as theta continues to increase, we're going to get down to that minimum of -1, which takes place at 3 pi over 2. And then we're going to keep coming back here, okay? And this would just repeat. I could keep going if I wanted to, but I think that's a helpful little visualization of this. Now let's bounce over and let's look at the cosine graph, and then we'll spend a quick second talking about the differences between the two. To give you the same little spiel, we know that cosine of theta is equal to adjacent over opposite. It's how we've been defining it since we were first introduced to these trig ratios. But we call our adjacent side now the x-coordinate, and we call that hypotenuse, r, for the radius. And once again, with the unit circle, I want to emphasize this, the unit circle is a helpful tool because r is always 1. So in order to identify cosine of a certain angle, all we have to do is look at the x-coordinate because our radius is always 1, and anything over 1 is itself. So in order to evaluate cosine of a given angle, we're just going to look at the x-coordinate. So if I come over here, once again, to 0 radians, our x-coordinate is 1. And then I rotate up here to pi over 2, and our x-coordinate is 0. And then I rotate over here to pi, and our x-coordinate's negative 1. And then at 3 pi over 2, our x-coordinate's 0. And then at 2 pi, we're coterminal with our original 0 radians, so our x-coordinate's 1. And what you're probably seeing, I kind of hope we're thinking through this critically, the only difference is that where we start, we're going to start at 1, versus with sine, we started at 0. So if I start at 1, at pi over 2, we go down to 0. And then at pi, I'm at negative 1, 3 pi over 2, and back up to a peak at 2 pi. So our cosine graph is going to look like this. If we're looking at it, once again, the only difference is where we start. When our angle of rotation is 0, when we're at 0 degrees or 0 radians, cosine has a value of 1. But all this other stuff's going to be the same. Our period is still going to be 2 pi. It takes 2 pi to get through this full cycle right here. Our amplitude is still going to be 1. We still got that maximum of 1. We still got that minimum of negative 1. Our domain is still going to be all real numbers because this graph could keep going. It's periodic. It could keep going forever to the left and forever to the right. And then our range is from negative 1 to positive 1. Now, once again, I'm going to bounce back over here, and I'll be brief this time. I'm going to get a look at our cosine graph. So now we start off with that x-coordinate, that blue horizontal distance being 1. And that distance is going to start off by decreasing until it gets to 0. That horizontal distance, that x, which is what we're graphing, is now 0. And now our horizontal distance is negative. And then it's going to work its way back up to 0. And then it's going to end at 1. So you see, really the only difference between sine and cosine is where you start. Now, let's tie a bow on this thing by looking at our compare and contrast, okay? Now, y equals sine x, it starts at the origin. I've got my sine graph shown here in red. It starts at the origin versus cosine, and that's kind of getting chopped off on my thumbnail, but cosine is going to start at a peak, or 1. It's going to start at 1, as you can see right there. From there, what's true about both of them is they both have a period of 2 pi. The domain for both is all real numbers, and the range goes from negative 1 to 1. The only difference is where they start. Here's how you can remember it. You ready? This is going to be stupid, but you'll remember it forever. Sine starts at 0. I know it's not quite alliteration or consonants or whatever, but sine starts at 0. Now, in our later videos, we will actually take some time and look at how to do transformations of these graphs. These periodic functions are actually really applicable in a lot of different ways. Anytime we have something repeated over time, we can model it with sine or cosine. But for now, we just want to have the base idea of where sine and cosine graphs come from and why they look the way they do.